diffraction of the light was being explained. Then coming to the explanation of diffraction on the basis of the wave theory of the light. So ultimately we need to discuss about the wave theory of the light, how this wave theory, Huygens explained about the wave theory. So the wave theory of light had its begins in Huygens' attempt to explain the double diffraction of light crystals in 1670. So we have taken the experimental by taking the crystal and how the refraction of the light is going to be taken place. And he also explained the principles that how this wavefront becomes a source of secondary wavelengths and the new wave front in the envelope of this secondary wavelengths. So in this Huygens explanation, we have done the experiment on diffraction. So what this is going to help us to show that the wavefront was such that only propagation is in the forward direction was possible. Hence, there could be no bending of the light beyond the shadow. So, bending happens when the wave propagates. So, when the light falls on a material, so what happens? The light bends. So, the light bending beyond the shadow is that experiment they have done with the help of the diffraction. So, Huygens wave theory did not predict the diffraction of the light. For this explanation, one had to wait till young a British physician discovered the independence of the light. Okay, that is on in 1805, which he explained successfully on the base of the wave theory of the light. The first satisfactory explanation of diffraction of the light was given by Frenzel. So was Frenzel and Fraunhofer. So Frenzel explained very good explanation about the diffraction of the light. So a few years later, using the wave theory of light, Frenzel combined the ideas of Huygens with the principles of interference and successfully explained the diffraction pattern obtained by several simple types of objects and aperture. His article on diffraction won him the prize of the French Academy. So in this lesson, we shall describe the Huygens theory of diffraction. So yesterday, I was keep on explaining how this electromagnetic theory of light was going to be used for math. So this is done yesterday. So today, we need to discuss about a simple mathematical approach for understanding of diffraction of light, the Huygens and Frenzel theory. So what is the Huygens principle and what is the principles of interference? So here we need to understand how this is going to explain the diffraction of the light by Huygens and Frenzel theory. So Huygens explained about the wave theory and Frenzel have done the experiment because of the Huygens theory, that is wave theory. Further, he could done with the help of the diffraction. So let us go a little further. So the principles of interference of the observer and the principles of superposition. Huygens principles state that each point in the wavefront becomes a source of secondary wave and sends out secondary spherical wavelets. The wavefront at a later time in the envelope two of the secondary wavelets as they have moved out in the time field. So it is like good explanation and good theory, how they have approached, how they have. This is very important to understand to read the concept. So each point in two then becomes a source of secondary waves and their envelope gives the next position of the wavelength. Thus, the propagation of light is going to be explained in terms of the advancing wavelength. When one such wavelength reaches a point, we say that light has propagated from source to the point. It's a very nice way of describing propagation of the light. The propagation of the light is nothing but which is going as a wave and which the light is going to be giving the direction, how to flow, how to propagate of the light. When the wave front and wave fronts are infinite in extent and not obstructed, and the full wave front is allowed to proceed forward. Friends will try to think about what would happen when the whole wave front was not allowed further, but only a certain part which could get through aperture. So this is what how when the light is falling on a material, so how the light is going to be bent. In this way, we can see the light wave and emerging from a light source. So here, the lights which is falling on this material, how inside this material, how the light is going to be bent, how emerging from the light source, we can see it through this diagram. So wavefront at t equals 0, new position f, that is wavefront. So as experiment like Grimaldi's had shown, when the observation point P on the screen is well inside the cone, nothing strange happened at P, but near the edges of the shadow, diffraction band called fringes appears and the light in this region does not obey the straight line propagation wave. So the propagation law. So let us see how this the output which we are getting. So Huygens principle applied to secondary wave from a narrow opening. So inside this is happening like a circle because it reflects and reflection happens. So the principle says that which is forming as a circle and the output which we are getting as over this. So to explain diffraction, Fenton used Huygens' idea of secondary wave, starting out from every point in the part of the blueprint, which is not instructed to find the effect of the secondary wave. So he uses his principles of superposition. So this explains the bright fringe or a dark fringe. Fringe is nothing but circle. Fringes is nothing but circle. Okay. So depending on how the secondary waves add up, taking into account. So like this, the fringes is nothing but the circles. When the light falls on that, the fringes is going to be formed like a circle. Okay, the resultant of that might be bright fringes or a dark fringes depending on the secondary wave. Taking into account their relative phases. Thus, in the Huygens principle theory of diffraction, one calculates the diffraction pattern as the intelligence pattern due to very large number of waves coming from several points in the exponential of the wavelength. We can carry out this program for something that is a function. In the next three lessons, we shall conclude this lesson by explaining the usual classifications of diffraction phenomena in two types, namely the transit. Yesterday, I told you what are the diffractions of the two methods, that is Fraunhofer and Fresnel diffraction phenomena. The Fresnel and Fraunhofer diffractions. Let's see that what this is going to say much further. From our description, discovery of diffraction, the observation diffraction phenomena requires special arrangement of point sources. So darkened room, etc., this is not quite true. The diffraction patterns are also observed in some simple ways. For example, if one looks at a small source, a distance rectangle, for an ordinary piece of a cloth, say a handkerchief, one sees a regular pattern of light spots having in the source. So they are trying with a small experiment when the light falls. How and when, what happens, which is a diffraction pattern. So if a distant tube light is seen through a half-closed eye, so the light passes through the regular obstacles formed by the eyelashes. The set of diffraction patterns are seen. Looking through the narrow gap between two fingers and the tube light, one sees diffraction bands. Looking at one can find a simple way of classifying diffraction patterns. So the source of the light is, and the point of the observation P are a small distance in the diffraction screen. So they are just studying by taking the different materials and they are able to focus some light on that material and how this output is generating by falling on that material. So different materials, for example, light falls on some different material other than a glass, how the light is going to propagate, how the diffraction is taking place on that screen or the light falling on the diffracting screen from a beam or panel rays and the rays leaving the diffracting screen. That is the diffracted rays around the parallel rays. So one can call the Fraunhofer diffraction as diffraction. Due to parallel rays But this means that the source and the observation screen must be placed at infinite distance from the diffracting object. So a practical way of satisfying this seemingly impossible conditions is to place a source at the principal focus of the convex lens. So let us see the experiment. So now to study step by step. So let us see. So different materials, different diffractions are taking place. So when they have placed one material over here, so the diffraction, how it is bending and how the laser coming. This is a source and this is a observation. Okay. So in this way, different lines are not connecting. So here you can see how it is connecting. So the different materials, different diffractions and how it is combining together and coming as an observation as a particle. The sources and screen C are moved to a large distance. So the distance which is the, for example, these are the glass materials. So when the glass materials is placed in between a light, the source of the light is there. So how it is traveling? It is traveling like the source and which is allowing to pass in this way and we are able to see the observation. So how it can be connected. So with the different source, if the material is more far distance, how the source of the light is traveling, if it is near, if it is far, if it is away. So they are going to observe different diffractions and different conditions by replacing the lenses and moving from one place to another place. So they are going to observe the leaving sources that is S and screen C in their original position. So let us see further how this. So this is a Fraunhofer diffraction. One is incident wave. So when an incident wave is traveled to the glass material or a source which is helping to travel, this wave is generated to travel in this way. So output, we can see that one can use an ordinary spectrometer whose colorimeter and telescope have been adjusted for planet rays to study the Fraunhofer diffraction pattern of various objects by just placing the objects, statistics, etc. on the spectrometer table and observing the patterns through the telescope. So they are using different materials and they are observing and they want to find out how these patterns are changing, why it is changing. Even for the glass materials, okay, let us talk about a glass material. The glass material itself only changing in a different patterns. If I'm taking a plain glass, how the reflection and refraction is taking place. If I'm taking a wafer, how the reflection and refraction is taking place. And if I'm taking a prism, how this reflection and refraction is taking place in the glass material only, it is taking so much of different patterns and different directions and reflection and refraction is happening. If we are going to conduct different material, definitely we are going to have different output, right? So this is what they are trying to explain and do the experimental to find out how this light is propagating in a material, how the output is reflecting and refracting and able to get as a proper output. So this is a observation was done with the spectrometer and with the spectroscopy by observing the patterns through the telescope. Through the telescope, they could observe. So as shown in the figure, lens L forming the images with the point source located at infinity on the screen. So this is being explained how this construction and working of the lenses, that is L1 and L2. So the lenses have been taken for the L1 and L2. These are the two lenses where we have already have explained about that. So these two lenses helping to find out the sides of the AB of the focal length equal to the SL and LO respectively. Then L1 produces parallel rays which are incident on AB and L2 focuses on the diffracted parallel rays in its focal plane. But this is just a way of transfer diffraction. So there is an important conclusion to be drawn from what we have found out just now. In optical instruments, where an image of a certain object is found in the lens. Say the image of a star is an astronomical telescope. The image is really the Fraunhofer diffraction pattern of the apparatus which resists light coming through the lens. Okay, so the Frenzel and Fraunhofer diffraction mathematical approach. So this is being calculated by observed through a telescope and through with a spectrometer. So now they could understand, okay, when the light is falling or when a wave is falling on a lens material, so how the we can see it is flowing in one direction. Everything is flowing in one direction and it is interference is happening over here. So this is what they could observe through the telescope and by using the spectrometer by ordinary rays. So how the diffraction pattern of the various objects are coming and colliding with each other. So at this point, they are able to see that it is combining. All the waves are traveling through the lens. Or through the lens, all these waves are transmitted and colliding in one single point. So this is what the incident wave happened and they could observe. So this should be done in a calculation to find out. So that calculation part was explained here, Frenzel and Fraunhofer diffraction mathematical approach. So how this can be calculated? So for this distance, they are able to calculate. So for example, if they are taking this as an experiment and these are able to calculate, for the calculation part is very, very important for the physics because we are going to assume it is in the theoretical part. So definitely we need to be done with the mathematical calculation. So I'm taking this as a small piece. I'm able to fix a lens and I can calculate this in a manual. But if I want to take it in a bulk, the rays which are traveling a long distance, then I want to make it simplify and want to calculate. So this is what the mathematical approach will be taking place to find out the approach. So here we have taken the approach how to be calculated, how this Huygens wave theory is helping to find out the Frenzel and Fraunhofer diffraction. So here we are going to take a observation screen where the Huygens wavelet starts out from every point in the exposed portion of the incident wavelength. So and reaches P. We know that. So it reaches till P. We have to find the resultant amplitude due to these waves. According to the wave theory of the light, the intensity of the light. So why we stress intensity? Because when the light is passing on a material, so which is propagating and coming out as an output, the intensity of the light is very, very important. Because how the light is focused, according to that light, the intensity of the particles are going to be worked. That means the photons are coming out as an output. So the intensity to reach from one particle to the another particle. So we always talk about the intensity of the light will be proportional to the square of the resultant amplitude. For example, let us say a point Q is a source of secondary spectral waves. If the amplitude at Q is a the light disturbances at P, distance D away not shown in the figure due to the spherical wave is given by the formula. That is phi is equals to A by D cos omega t by kb, where omega is angular frequency, 2 pi f, where f is frequency, t is time, k is 2 pi f by lambda, that is wavelength, lambda is nothing but wavelength, omega t minus lambda d is nothing but phase. Ultimately, we want to find what phase. So we know that when wave is traveling, means a frequency will be the same, wavelength will be the same, energy will be the same, distance will be the same. Only the difference what we can find is nothing but phase difference between one wave to another wave. So the following Frenzel, we now add the light disturbances due to all the points between A and B so that the resultant wave is given by the sum. So that's phi is equal to sigma A by D cos omega t minus k of d since complete light O are continuously distributed in the AB That is, a resultant light disturbances may be written as an integral. So, in integration form, where we can write integration of pi dr is equals to integration a by d cos omega t minus k of d of r. So, where r is nothing but distance of t from the origin r in the diffracting aperture. Okay, from the basis of calculating the diffraction patterns in the simple way, and will be used in the next 3 minutes. At present, we wish to find a quantitative way of distinguishing between the Frenzel and the Fraunhofer type of diffracting patterns. Here, the size of the aperture, namely the distance, AB is equals to B is important. We shall now find an expression for the phase difference between the waves reaching B from the extreme ends of the opening namely the point A and B. That is a path AP equals to D. So path BP is nothing but D plus delta. So here delta is the path difference between, we are calculating the phase difference. Why I am discussing this specifically stressing, because we need to find the phase difference. So that's why this path A to P and path B to P is nothing. A is traveling the same distance, B is traveling the same distance, C will be traveling, B so on. So we need to find A to P, then path B to P will become D plus lambda. So lambda is the path difference and 2 pi of the lambda is the phase difference for waves from A to B. So A to B we are calculating, reaching B. Let us find an expression for delta using the well-known relation between the sides of the triangle, that is ABP. So D plus lambda whole square is becoming D square plus B square, that is equal to 2B D cos pi by 2 plus 0. So when theta is the angle between AP and the normal for the split AM, simplifying 3.3 we get here. Okay, please go through that 3.3. Okay, then we are going to get the path difference. Here we are going to find the assumptions when generally holds in practical situations. Namely, delta is less than B, which means that P is sufficiently far away from AB. Thus, in equation 3.4, we may ignore delta square in comparison with 2 delta D. So this 3.4 becomes 2 delta D, that is equals to B square plus 2P beta sine theta. So here we are going to find ultimately the phase difference for A to P and B to P. So here the conditions of observing the Fraunhofer diffraction. For small values of D, the other term B square by 2D becomes important. We can write delta by this delta infinity is equals to B square by 2D. So for the smaller values of D, the phase will have a part varying as B square. So here we are going to find the Frenzel and Fraunhofer pattern. By the dividing line we want is then by given by. That is nothing but the path difference. So here we have the equations to find the Frenzel and Fraunhofer diffraction of the boundaries, large values, smaller, and here very small values. That is when it is far, when it is near, when it is sharp, when it is shadow. So we are able to find all these lines, propagations, and observations. This can be summarized as follows. The Fraunhofer diffraction is square by L lambda is greater than 1. So the Frenzel diffraction b squared by L lambda is equals to 1. Straight line propagation, that is b squared by L lambda is greater than 1. So the value of dimensionless constant b square by 2 lambda decides the type of diffraction to be seen. We shall illustrate the thing with an example. Let a beam of parallel rays of wavelength, that is lambda, equals to 6 into 10 to the power of -5 centimeters fall on the opening of the window. So this is what is being explanation done with the Fraunhofer and Frenzel and Fraunhofer. So this beautiful experiment can be performed easily with a He and laser. So consider these values and corresponding values. So corresponding values, that is b squared by L lambda, are 17 and 1.7 is 0.0017 respectively. So we expect a sharp shadow obeying the law of light. Line propagation in case I. Frenzel diffraction pattern showing fringes near the edge of the shadow in case 2. And finally, a Fraunhofer diffraction pattern consisting of a bright spot in the center, surrounded by the fringes in case 3. Notice that the slit of it 0.01 centimeters, one can produce a Fraunhofer pattern at a speed just a meter from the shadow. This beautiful experiment can be performed in the He HENE laser. So summary. So let us see that. What is the summary says? This diffraction of the light was explained on the basis of the Hindle's discovery, Newton's works, and the wave theory of light. The two types of the diffraction are Frenzel and Fraunhofer. In Frenzel type of diffraction, the source of the light and the point of the observation is a small distance from the diffracting screen. So in Fraunhofer type of diffraction, source and points of observations are very far from the diffracting screen. So this is about the Frenzel and Fraunhofer diffraction. So coming to the next, that is Frenzel diffraction and a straight edge. So this explains about how the straight edge is helping to find out and what will be the mathematical treatments of diffraction effect at a straight edge. So that is about objective interaction, mathematical calculations of the diffraction at a straight edge. So it's a simple topic, not much complicated, easy. So here we have objectives. Explain the Frenzel diffraction at a straight edge. Understand the Huygens Frenzel theory of diffraction wavefront on a straight edge. Find out the amplitude and the phase of the wave reaching the screen from elements in the wavelet. The resultant disturbance is at a point on the screen. So this is about the introduction and the mathematical treatment of diffraction at a straight edge. Okay, just a second. Yeah. Coming to the mathematical treatment of diffraction at a straight edge. So before going to that, let us see the introduction. Because the introduction is very, very important. We need to know why they have discovered or they could find through these experiments. So diffraction phenomena is a characteristics of wave motion as we have seen in the unit 3. That is, diffraction is noticeable when a wave is distorted by an obstacle which has dimensions comparable to the wavelength of the wave. The obstacles may be a screen with a small opening or a slit, which allows only a small portion of the incident wavefront to pass. In this unit, we shall study the further diffraction at a straight edge. So, before topic in the third unit, what we could understand why we are going little further because when the light is falling on a material, all that material is coming as a wave and combining together as a particle P. The observation we can see that as a one wave. So it is splitting, the light is falling on a material, it is splitting and again it is combining as a one. one line, right? So now we want to find out Fresnel diffraction at a straight edge. So straight edges. So we need to find at the straight edges what is happening. So here directly we are going to find out the mathematical treatment of diffraction at a straight edge. So this is an experiment being explained. How this we are going to apply. We apply the Huygens Fresnel theory to Fresnel diffraction at a straight edge. Shows the straight edge, that is OS, is extending to large distance beyond S. A plane wave front is incident from the left. Its portion along OS is completely stopped by the straight edge, and the part extending along OQ and beyond is allowed to pass. So here we need to go with the diagram. So here O and Q and S is being there. So how this is the edge. Okay. So the source we can find. So we can find a straight line at the edge, right? This is a P is nothing but observation. S is nothing but the source. When the light falls on a material, so how the straight Fresnel diffraction is straight edge. Directly it is falling on a straight edge. So here we can see the light disturbance is reaching the point. Disturbance is reaching the point P from Q. E is represented by. This is what we could find out. D omega is equals to dh cos omega t minus delta or theta, where theta is equals to 2 pi by lambda. We know that h square by 2 of s represents the phase, because we could find what ultimately in that third unit we can find the phase difference. So the sources is coming out in the light. So from first wave to second wave, third wave, fourth wave, we could find what everything will be the same. It is and the light falls on a material, everything, the frequency, the wavelength, the energy which is been transmitting, will be the same. The only difference we can find is, as I told you, phase difference. So we could find the phase difference calculation mathematically we could calculate. So now we are going to find for the straight edge also. So this is helping to find simple harmonic waves. So we shall use this vector, or it's sometimes called phase, or the method. The wave discussed by expressions, that is 4.1 is represented by a vector whose length is proportional to the amplitude and whose direction with reference axis is equal to the phase. So shows the vector of the length, pH making an angle theta, that is equals to 2 pi by lambda, that is h squared by 4s with the x-axis. So the x and y components of these small vectors are dx is equals to dh cos of 2 pi by lambda, h squared by 2s, dy is equals to dh sine 2 pi by lambda, h squared by 2s. So here we can find the vectorial representation of the wave. So what is the vectorial representation of the wave? So here we can see the diagram says the resultant x component of A and the resultant y component of the B. So 0 to h. Okay, here we can find for A and B. And that is about 2 pi by lambda h squared by 2s. Here by using the Huygens secondary sources in the wavefront between O and the Q. So here we can see O to Q. So the distance is nothing but r. We are able to find. Okay, the resultant amplitude produces at the point B is equal to the length of the resultant vector of phasor, that is r, is equal to root of a square plus b square, that is nothing but we are going to find the distance. So we need to find the distance for one place to the another place. So in previous topics, we could find the phase difference. Here we are able to find the distance. Okay, the phase of the resultant is pi. Note that the point D represents the resultant of the disturbance from elements along O to Q, that is H, reaching diffraction screen. As the length OQ is increased, the point D moves along a curve equations 4.2, 4.3. are the parametric equations describing this curve, where h is the length OT along the curve. Let us find the shape of the curve as h becomes very large. It is convenient to use a new variable b instead of h defined by b is equal to h of 2 by delta s. So equation says about dx dy and further let's choose now x and y. So here we can find we will write this new variables x and y also as x and y. So no confusion shall arise us. So this the slope of the curve b dy by dx that is equal to tan pi by 2 v square and the angle of the slope. So here we are going to find this angle of the slope. So we are finding the distance, we are finding the angle of the slope, everything can be calculated and using this mathematical calculator. So here the integrals x and y are known as Fresnel integrals and the curve is called a Cornus spiral for negative values f of v. There is a lower branch of the spiral ending in the asymptotic point z at x is equals to minus 1 by 2 and y is equals to 1 by is 1 by 2. So this is Cornus spiral. So we can find this Cornus spirals also we can calculate. So this reason of choosing this VI cap instead of V cap. So is a universal parameter and can be calculated for a given problem. So this is what we can say that the resultant amplitude can be calculated by using this corresponding method for finding out the ends of the um, vectors and the spirals, that is coordinates, that's x is equal to 0, y is equal to 0, and this is the origin. So this calculation is so interesting. If we are finding, for example, we are going to find the coordinates, x-axis, y-axis, and z-axis. So I want to find, for example, a material is there. When light falls on that material, for example, photoelectric effect we have taken. So I just want to find how this is generating the charge. Okay, so electrons will be there. All the electrons starts vibrating and radiating. So I want to calculate with the help of one single particle I have taken. I am able to calculate for one single particle all the three axes. So all the three axes will be transmitting the energy from one particle to the another particle. That might be front, back, that might be in a cubical structure we can take and we can calculate. So that is what they are trying to explain this amplitudes as a point taking x-axis, y-axis, and z-axis. Okay, this is what is about explaining of the particles. So how the particles can be calculated from one point to the another point, how it is being transmitted. So the upper limit is still v is equals to infinity point z as v double dash moves of the point A to and the spiral moves. So how the energy is being transmitted, how this can be taken place. This is about the Fresnel diffraction at a straight edge is explained, taking plane wave from plane wave front to incident outer edge. Formula for the amplitude and phase of the wave reaching the screen from the elements in the wavefront was developed. Okay, this is about straight edge. Next. Next topic will be the plane diffraction grating. So very important. We need to know what is grating. Plane diffraction grating measurement of wavelength of the light. So plane diffraction grating measurements of wavelength of the light. So objectives, introduction, Fraunhofer diffraction pattern of single, double, and multiple slits. So different slits, different variations can be taken place. So we need to observe this. So before going to this topic, I just want to discuss much about grading. So how this grading takes place. So today I am going to discuss the basics of the grading. So once this basics of the grading can be discussed. If I'm able to help you out by understanding about what is grading, how this grading takes place, then you can easily understand the topics whatever being discussed over here. Okay. Coming to the topic, that is plane diffraction, grading measurement of the wavelength of the light. So I just want to discuss much about grading. So what is grading? Why we need to discuss about grading in physics? In general term, we know what is grading, but we need to discuss much about in physical language, physics. So why this grading helps to find out the light. Okay, so we know now what is diffraction. So diffraction is nothing but which is coming out as a light which is being diffracted and coming out as a one particle. That is grating is an optical element. We call grating is an optical element that divides, okay, disperses light composed of lots of different wavelengths. That is example. For example, if we take a tube light. So the tube light have done with the grading. So nothing but which is traveling. The white light is traveling in different ways. So for example, light components by wavelength. So in a simplest type is nothing but grading is one with a large number of evenly spaced parallel slits. Okay. So what is grading slit? We need to know. So on the time diffraction will be added with the grading. Whenever we are talking about the grading, without diffraction, there is no grading. So a diffraction grading is a large collection of evenly spaced parallel slits that produces an interference pattern similar to the but sharper than that of a double slit. So this is about a grading slit and what in general we call grading is nothing but we can say that is nothing but a means in normal language if we talk about grading in general. Grading in general meaning. What is grading in general meaning? So nothing but sounding harsh or unpleasant. So which irritates us by listening that sound, we get irritation. Grating is nothing but which is making unpleasant sound is nothing but which we are unable to hear. It irritates is nothing but grating. Okay. So, but in physics terminology, by using the diffraction, which is helping us to produce a optics. Okay, means a wave, dispersion of light. A dispersion of the light which is helping. So grading takes place when equal mixtures of red and blue colors. Instead plain wave is there. Okay, grading means which is being divided. So from that light which is being traveling as a source and we are able to find the different levels of colors. Different colors we can find out. So that is what is about diffraction of grading. So this is about diffraction, grading, and definitions and the formulas can be we will discuss in tomorrow's class. So all the topic this topic much it will be explained about completely about the grading, principle of grading. We need to know all this. So how this diffraction grading is helping. So in general terminology, we can say that A diffraction grating defines an optical component with a periodic structure that splits the light. So you need to understand, I'm trying to explain you in a general, easy way. So which is splitting of the light into various beams that travel in different directions is nothing but a diffraction grating. And just repeat, a diffraction grating defines an optical component with a periodic structure that splits the light into various beams that travel in different directions. So we can also say that in alternative way to observe the spectrum other than in prism. So spectrum from the prism only we get the spectrum lines, right? So what we are observing is nothing but a spectral lines. So when the light is incident on the grating, the splitting light will have a maximum at an angle theta. So that is what is about the grating. So how this is grating takes place, how this, now we are able to see everything in a color. So with the help of this explanation, observation, reading, finding, we are now using this technology very vastly and we are enjoying like anything because of the advance because in those days they have only monochromatic lights that is black and white. Nowadays we are using advanced technology because of this theory, this calculations, these observations, this understanding, explanation, everything efforts were done by them and advanced technology was developed. Research is happening continuously, but the methodology will be applied by these experiments only. So this is about a plane diffraction grating measurement of the wavelength. So I hope that how this grating takes place. So a light falls on a material which grating takes place means a single slit is helping to produce large number of rays. That is, we call it as grating. So when the light falls on a one material, from that plane, multiple spectral lines are coming out. Is nothing but proper, like how the sound waves are filtered, how, for example, to explain you more clearly, what is grading. So if we are taking a sound wave, filtration is being done. If we are taking current, filtration is being done. In such a way, grading is also being done. And to get a proper output of the light or the spectrum through the material, grading is done. This is the best example how this grading takes place. So this topics, how this plane diffraction grating measurement of wavelength of the light. This is so simple if you understand how the grating takes place. So introduction, already we have studied principal and Fraunhofer type of diffraction. Let us consider the diffraction pattern produced by several parallel slits of equal width. B equal the space and the distance A. This unit we should discuss the constructional use of the plane didactic grating. So how the filtration takes place. The light also, from the light, whatever we are taking as an output, grating will be done. So Fraunhofer diffraction pattern of single and double and multiple slits. So this is the experiment. We're taking single slit, double slit, Fraunhofer diffraction pattern of single, double and multiple slits. So here we can see the diagram, sources slits and diffraction slits. And from these slits, how the grating takes place and how the grating filtered output we are going to get. This has been explained. Of the bar grating is never used in spectroscopy, where grating with N or the other 1006 per centimeter is required. Ingeniously, methods have been employed. So this I will discuss in tomorrow's class, how this gradient takes place, how the diffraction is taking place, diffraction spectra. So now we are going to talk about the spectral lines. Diffraction spectrum in various orders. Very interesting. There is only cover and discussions of the grading. Oh, I'm just going through this, what are the topics should be covered. Lockery, the polarization. Very interesting. So tomorrow we'll go a little faster and day after tomorrow we'll talk about discuss about polarization. The polarization for the polarization by reflection. So I just want to cover all the topics, not going so depth. So if we go to the depth, it will be like research. So we need to understand the concepts, how it works. So most of the thing is like it's theory only, theoretical. Also. Okay. See you all tomorrow. We'll discuss much more further.